All right, so buckle up, everyone, because today we are diving into something pretty mind-bending. We're talking about, you guessed it, synthetic curvature theory. Yeah, SCT.
Wow, jumping right into the deep end, huh? Love it.
Absolutely, no time to waste. Now, just to set the stage here, SCT basically suggests that curvature, that thing that makes space all bendy and weird, like around a black hole, well, might not actually be a fixed property of the universe. Instead, it could emerge, get this, from the interaction of, well, everything, like how things resonate with each other.
Yeah, it's a huge shift in perspective. I mean, we're used to thinking about geometry as static, right? Like a circle is a circle, a square is a square. But SET comes along and says, hold on, what if those shapes are actually just snapshots of a much more dynamic process?
Okay, so let's break this down. We got this research paper from Moonshot Labs titled Synthetic Curvature Theory, a resonance-based framework for geometry fluid intelligence by Richard Aragon and Ash Kelly, and is filled with some pretty wild ideas.
Oh, yeah, this paper is a trip, for sure. Aragon and Kelly, they're really pushing the boundaries here.
So starting with the basics, what exactly do they mean by resonance? Is this like good vibes, bad vibes kind of thing?
Oh, not exactly. Think about it more like an orchestra tuning up, right?
Hmm.
Each instrument has its own frequency, its own sound wave, and when those waves interact, they interfere with each other.
Okay, I'm following so far.
So SET proposes that curvature in space emerges from a similar kind of interplay, but instead of sound waves, we're talking about the fundamental frequencies of, well, everything. Particles, energy fields, even consciousness, who knows?
Okay, so instead of space being inherently curved, like imagine a pre-bent bowl, SET is saying that the curvature actually pops up depending on what's happening inside it, based on how everything's vibing together.
Exactly. It's like the universe is constantly tuning itself, and the curvature of space is the result of that tuning process.
Whoa, okay, that's pretty wild. So how does this idea of resonance actually play out in terms of different geometries? We've got Euclidean geometry, the kind we all learned in school. Then there's hyperbolic geometry, all those crazy saddle shapes. And then you've got fractal geometry with its infinite repeating patterns. How does SCT fit all these together?
Right. So the paper uses this term, synthetic hyperbolicity, Euclidity, fractality, to show how different geometries could be, well, simulated through resonance.
Okay, so walk me through this.
So, for example, hyperbolic geometry, all those saddle shapes and stuff, that emerges when frequencies are diverging, moving away from each other. Then you've got our familiar Euclidean geometry, that's the flat space we're used to, and that happens when frequencies are stable and coupled together.
Hold on, let me try to picture this. So if our universe is like a giant orchestra and things aren't vibing together, we get all these weird curves and bends in space.
Yeah, that's a pretty good analogy. It's like when the orchestra's out of tune, space gets all wonky, and then there are fractals, those infinitely repeating patterns. The paper suggests they emerge from recursive harmonies, frequencies nesting within each other, creating these self-similar structures across different scales.
Okay, so we're not just stuck with one type of geometry. By tweaking the frequencies, we could potentially shift between them.
Right, like imagine being able to switch between different musical keys, but instead of changing the notes, you're changing the very structure of space itself.
This is where my brain starts to melt a little bit. So what does all this have to do with intelligence? The paper mentions AI using these synthetic curvature fields, right?
Yeah, that's where things get really interesting. So imagine these curvature fields as landscapes that guide how AI learns and makes decisions. The paper introduces this equation, it's equation 2 in the paper, called the synthetic metric tensor.
A synthetic metric tensor, huh? Sounds complicated.
Well, it is a bit technical, but basically it defines distances in this resonant space, meaning it tells you how far apart things are based on how their frequencies interact.
Okay, so like in this resonant space, things with similar frequencies would be closer together, even if they're physically far apart.
Exactly. So an AI could navigate a problem like, let's say, finding the optimal solution to a complex equation by adjusting its own frequency. It's essentially changing its position in this resonant landscape to find the solution more efficiently.
Whoa! So by tuning its frequency, the AI is essentially warping the space around it to get closer to the answer.
You got it. It's like reshaping the maze while you're still inside it. And it's not just about problem solving. The paper also talks about how these synthetic curvature fields could play a role in, like, Memory formation, pattern recognition, even consciousness itself.
Okay, my mind is officially blown.
Yeah.
So this RCF thing, the resonant curvature function, it sounds like this is kind of a key piece of the puzzle. What's its significance?
The RCF, it's described by equation 1 in the paper, and it's really the heart of the whole theory. Basically, it says that curvature at any point in space depends on the differences between the frequencies present and how the overall harmony is changing.
So we're not just talking about individual frequencies, but also the relationship between them, how they're all weaving together.
Right. And the RCF gives us a mathematical tool to actually measure and predict how curved space will be based on the frequencies at play. It's like having a ruler for measuring the curvature of reality itself.
This is getting pretty deep.
Mm.
So if we understand this resonant geometry, could we actually create AI that can, like, warp space to solve problems faster? Maybe even problems we can't even wrap our heads around right now.
It's definitely a tantalizing possibility. I mean, imagine AI that could, like, fold space to bring distant data points closer together or create shortcuts through complex networks. The paper even hints at some even more mind-blowing ideas like synthetic topological phase transitions and multi-agent coupled curvature fields.
Okay, you're going to have to break those down for me.
So, synthetic topological phase transitions. That's basically talking about how an AI could potentially switch between different geometric states, kind of like how water can change from ice to liquid to vapor. And then multi-agent coupled curvature fields, well, that's where things get really interesting. That suggests the possibility of multiple AI systems coordinating with each other by changing their shared geometric space, like a collective dance of warping realities.
Okay, whoa. So just to try and wrap my head around all this, SET is suggesting that curvature might not be a fundamental property of the universe, but a side effect of how everything vibrates, how everything's in this constant state of resonant interaction.
That's the gist of it, yeah. And if we can learn to play this cosmic symphony, to understand and manipulate those frequencies, who knows what we could achieve.
Yeah, and that's what makes this deep dive so incredible. If this has sparked your curiosity, definitely check out the full research paper from Aragon and Kelly. You'll be amazed at what you discover. And who knows, maybe you'll be the one to unlock the secrets of this resonant reality. Until next time, keep those frequencies high and those minds open.
Absolutely. Keep exploring, keep questioning. That's what it's all about.